Okay, welcome everybody. All right, so what we're going to do is we're going to review chapter 10, I guess it's in the Nelson Physics textbook, which was, or 9 and 10, I guess, which was waves, sound, and wave applications. Okay, so just a review of what we've done so far. I think we talked about velocity of sound, correct? Yeah, we did this. So 331.4 meters per second plus 0.606 times t. We did this. Okay, we did Mach number, which was velocity of object divided by velocity of sound at that spot. Correct? And then what else did we do? So we did this. Well, we did strings. We talked about fundamental frequency. We talked about nodes. We talked about antinodes. We talked about our formula, length, which equals to n divided by 2 times lambda. Okay, length of the strings. Now remember, this was 1D. Strings are in 1 dimension. Okay, not 2 dimensions. So this was pretty straightforward. Okay. We also talked about what happens to velocity when, or frequency of a string vibrating when the thickness and diameter and all that stuff, right? So we did that review as well. So for this one, what else did we cover in chapter 9 and 10? That we did cover Doppler effect. Okay, so let's do Doppler effect. Okay, what is Doppler effect? Yes, who can tell me what Doppler effect is? Yes, what was Doppler effect? The apparent change in frequency, okay, of sound or of a wave. Okay, depending on the motion of the object and or the observer. Okay, so the apparent change, of course, basically means that as the sound or wave gets closer to you, the sound seems, or the frequency seems to increase, and as it goes away from you, okay, your frequency decreases. Apparent change in frequency, right? Now we came up with, there was a whole bunch of formulas that we used to describe this change in frequency. Yes, what were they? Do you remember? So it was F apparent, which equals to F observer times V of sound divided by V of sound plus minus V of object. Okay, now when was this? We would only use this formula if the observer is standing still. Yeah, we will. Now remember, most likely when you get a question, the velocity of the object, this is note to self, might be in kilometers per hour. So you got to make sure you convert the kilometers per hour into meters per second. Okay? You'll have to also figure out the velocity of sound at that point. So if the temperature was 25 degrees, you'll have to calculate that velocity of sound. And this is from the object itself. So the frequency, I guess, released from the object. Okay, so the frequency that is emitted from the object itself. Now that frequency can only be changed by the object. So this is the apparent change. This is what the observer is hearing. Okay, so now remember, frequency of course is measured in hertz. Cool. Okay, so this was the first formula that we looked at. The second formula that you had for Doppler effect was when either or of the two are moving. Okay, so you had F apparent, which equals to F from the object. Okay, and this was velocity of sound. What was it again on the top? Plus V observer plus minus divided by velocity of sound plus minus V of object. Now, one thing I forgot to mention. So if either observer and or object moving. Now, one thing I forgot to mention in the last formula was we subtract when object moving toward observer. So if the object is moving towards observer, then it'll be V of sound minus V of object. Okay? Otherwise, it will be add V of sound plus V of object. Can I erase this part right here? Okay, so otherwise we will add V of sound plus V of object when moving away from each other. Okay, now also we have the same effect in light as well. In light we call it a blue shift if it's coming closer, and a red shift if it is moving away from the observer. Yes? Highly unlikely, because we didn't really talk about light. But if it comes, at least you know that that's what it's going to be. Blue shift coming towards. Blue shift is the higher end of the spectrum. Coming toward observer. This is for light. Okay. And red shift moving away from observer. So we talked about Doppler effect. What else did we talk about besides this? The one thing that we're missing, I think, there was one more, open and closed air columns. Yes? Yeah, same thing. This is when the sound, so imagine this is an ambulance that's moving towards the observer and the person is walking towards the ambulance. Does that make sense? Yeah. Okay. Okay. Can I erase this? Yes? Okay. Alright. So let's erase this. Okay, so the next thing that we talked about for standing waves was we talked about mechanical resonance. Okay. Mechanical resonance, example, as we said, was a wine glass exploding or breaking down due to it absorbing the, due to it vibrating at the same frequency as its own regular frequency. And we talked about the Tacoma Narrows Bridge, which collapsed because of that same principle as well, mechanical resonance. Now, when we're talking about mechanical resonance, all acoustic instruments, especially drums and so on and so forth, also use a similar principle. Okay, so we talked about open and closed air columns. Okay, now an open air column is open on both sides. It's known as an open air column. A closed air column is closed on one side only. So this is a closed air column. This is an open air column. Okay. Now we talked about what the fundamental frequencies and all those nice things were when we're talking about open air, closed air columns. So let's start with an open air column. So we said in an open air column, my fundamental frequency starts out like so, which is 1/4 plus 1/4 lambda, which gives you half lambda. Now this is the first harmonic, also known as the fundamental frequency. Okay, and then we keep on going up by half a lambda. Okay, and so the next one, of course, is going to be okay, now I can't even draw. I've forgotten how to draw. Like so. There you go. Okay. So that's 1/4, half, 1/4, which gives you 1 lambda. It goes up by half a lambda. Second harmonic. And also known as the first overtone. Okay. And then we continue to the next one after that. Okay. And we get something like this. Okay, 1/4, 1/2, 1/2, 1/4, which is 1.5 lambda. Third harmonic. Okay, second overtone. Okay, now remember that you have nodes, nodes, node right there, and then antinode, antinode, antinode right here, and so on and so forth. So that's an antinode, there is a node. This was for open air columns. Okay. Are we good with this? Go to the next one, which is closed air columns. Can I erase this? Yes. Okay. So closed air columns, very similar. So you had closed on one side, okay, and in this one we start out with 1/4 lambda. Okay, this is your fundamental frequency. Okay, also your first harmonic. And you had one node and one antinode. And again, we started going higher by 1 lambda, half a lambda. Okay, so you had half plus 1/4, and you got 3/4 lambda. Okay, so this was 1/4 lambda right here. This is your second harmonic, and also known as the first overtone. Okay, then we did the same thing again for the next one. Remember, the size of our object is not increasing. Okay, so half lambda, 1/4 lambda, also known as 5/4 lambda. Third harmonic and second overtone. Okay, remember node, 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 antinode, antinode, antinode. Same thing here, node and node, antinode and antinode, and so on and so forth. So this is chapters 9 and 10. Anything else that we missed out in this chapter? Well, the video is ending, 10 seconds left. Okay, which other formula? So we did that in the